so you don't have to worry about anything. Even if it is, this is just a magnetic field that is given. Okay. Quickly just copy the name or just take the screenshot because time is.
This will take. I'm done. I'm done.
All right, Rani. So then I'll stop here. Okay. Now we are left with one topic, induction, that I'll complete in the next class. All right.
Okay.
Okay. All right. Thank you.
Mm.
Yeah, Jesleen Muniba, am I audible to both of you?
Yes, ma'am.
All right. So good evening. Let's start in the last class. We were discussing phasors, phasor diagrams were done, AC circuits having only resistors, only inductors, only capacitors were completed. So we didn't practice any numericals based on this. We did all the kinds of derivations. So please practice these derivations. They do come in the exam. This part only we have completed. Any doubts still here, class? You all are not submitting the assignments. Let us start sharing the assignments of alternating current. I told you in the last class. See, this is a quick summary, a quick revision of what we've studied in the last class. Okay, then we'll move on to the numericals and then to LCR circuits. Straight away, we'll start with series LCR circuit. So, IRMS is equal to I naught by root 2. We have derived this also. So, when we have a circuit having only the resistor, we know one thing, that if the resistor circuit is there, EMF and current both are in the same phase, because you can see phase difference between them is 0. So E is equal to E naught sine omega t, I is equal to I naught sine omega t, and E and I are in the same phase. So I naught will be equal to E naught divided by R, I RMS is equal to E RMS divided by R. This is all about the circuits having only resistor. Then the circuit having only the inductor. So E is equal to E naught sine omega t or E naught sine plus omega t plus pi by 2. So current is I naught, I is equal to I naught sine omega t minus pi by 2, or minus won't be there. This can be added over here. Anyways, this shows that current lags by 90 degree, voltage leads by 90 degree. And here the resistance that we get is XL, whose value is omega L. So I naught is equal to E naught divided by XL, IRMS is equal to ERMS divided by X. When we talk about the circuits having only capacitor, E is equal to E naught sine omega t. Current is I naught sine omega t plus pi by 2. So current leads, voltage lags in this case. Okay, current leads by 90 degree, voltage lag. Here the resistance that we have is the XC, capacitive reactance, and value of XC is 1 by omega C. So I naught will be equal to E naught by XC, IRMS will be ERMS by XC. The way you treat normal current and normal resistance using Ohm's law, here also you are going to use it. So I RMS is I naught by root 2, E naught by root 2, XC can be written as 1 by omega C, which is ERMS by XC. Straight away remember, the way we write current is equal to voltage by resistance. So resistance depends upon the cases, whether it's EMF or it's XL or it's XC, depends on the case. This is a summary of what we've done in the last class. Quickly just make it in the tabular form only like this, so that whenever you revise, you have all the things together written, and then we'll come to the numericals. Okay, please write it. Yes, who is this? Fatima 12-1?
Ma'am,
Yes. What's your full
I
name?
did it that Fatima, ma'am. Fatima Tajunisa.
Okay, all right. Okay.
Ma'am.
Yes, Fatma.
I'm just joining today, ma'am.
Yes, Fatma. See, actually, there are two batches going on. So, in the next batch, I think you must have received the ID or you will receive it. There is one more batch where your first book will be completed. Okay, you continue here, whatever you are able to understand, because see, we are in the middle of a chapter. So teaching you, this is a summary what they are writing, what we've already done. So teaching this part will not be feasible for me. You study, you continue with the class, see whatever you are able to understand. Wherever you have any trouble, you let me know. I'll try to explain you that part. But don't worry about what has been already completed. In the batch, the next batch in which you will be joining, the complete backup will be provided to you. So more or less, we'll focus on completion of EM waves chapter and the second book here thoroughly, but the half of AC will be done here because from mid you are joining today. But rest of the first book you will be given the back of till your this chapter AC. Okay, so you can continue and backup will be provided. And for the fresh chapters, you can continue from here itself. That for that you won't require the backup. Okay,
Ma'am, what is the next chapter after AC?
EM waves, electromagnetic.
So can I join from EM waves because there'll be no use attending a class from mid of the chapter.
Yes, I feel the same too because from AC you can continue. Means AC, if you will continue, it will be in the middle. This is in the middle of chapter and a lot of has been done. So an AC is completely different chapter. So it will be difficult for you to understand what is occurring. You join from EM waves, but you join the backup class, Fatma. Don't miss on there. Okay.
Okay, ma'am.
All right. Okay
Uh,
then.
and ma'am, is EM wave connected with any other chapter?
EM waves is connected with the chapters, but you will be able to understand EM waves more. So, okay, because it's a very short chapter, theoretical part is more. So at least you can attempt it, attend the classes. If you have any trouble, you can attend it again in the backup class. There's no problem with that. But at least don't miss
Uh,
on the classes from the fresh chapter.
okay, ma'am.
Right.
The first batch, the second batch, when are they completing the syllabus?
In the second batch where you will be joining for the
Yes,
backup,
ma'am.
syllabus will be completed. See, right now we have completed the first chapter. Like we in today's class, we'll complete the first chapter. So in the next class, second will be started like this because it's a very recent new batch has been created for all the new students.
Mm.
So here we are having the classes. Actually, we go very fast in that class with the notes and all. We don't waste time because we have to complete the whole first book there.
Mm.
Okay, so you can take the backup here. You stay in this batch. There's no problem. But from EM waves, you can continue. So see, wherever
No,
extra
ma'am.
point,
What I'm asking is the
yeah,
second batch which is going on. When will they complete the syllabus?
they'll be completing in the same time. The syllabus will be completed within the same time. Means when this batch will be completed, December.
In the December.
Yeah, in the month of December,
In
because
the
you all will then have your pre-boards, no? So before your pre-boards, we'll try to prepare you.
Oh, okay, ma'am.
All right.
Okay.
Is there any timings issue, Fatma?
No, ma'am.
No, means with the second batch or with this batch, anywhere you find that problem with the
No, I
timings.
just can't get an assuring feeling that this will work out because it feels like everything is in the mid. That's what I'm thinking.
Okay, no, see, from in your second batch, no, the second batch, you join it today. There you will understand it better because more new students are there. So you join today. Today we'll start with a fresh topic only in the batch. So you see how things are going, and will you be able to cope up or not? Okay, in the second
Okay,
batch,
ma'am.
you can give a better feedback because right now it's in the middle of chapter. You will not be able to understand. Join today's class, then see how are you comfortable, or if you want any changes, or if I can help you separately, then you can tell me afterwards. Okay, let's meet in the next
Yeah.
class. Okay,
Okay. Okay, ma'am. Thank you.
all right. So, yes, class, let's continue with the numericals. This is a pure inductor of 25 millihenry is connected to a source of 220 volt. Now, source is there means this is VRMS given to you. That is 220 volt. Inductor means L is given as 25 millihenry. That is 25 into 10 to the power minus 3 Henry. Is connected to a source of 220. You have to find out the inductive reactance. Means what is XL and what is IRMS. If it says the frequency is given as 50 hertz. Now see, XL is equal to what? XL is equal to omega L. Omega is not given, but linear frequency is given. So you can put 2 pi into nu L. This is the formula we've already discussed in the last class. So XL will be 2 into pi is 3.14. Frequency is given as 50 hertz and L is given as 25 into 10 to the power minus 3. So this will be the resistance only. So unit will be ohm. This you can solve and see whatever is the answer. I think it will be 8.5 something, but you can cross check it. Now, what about IRMS? We have studied that IRMS is VRMS divided by the resistance. Now, what is the resistance of this circuit? Can anyone tell me? R is not given, then what should I calculate? What should I calculate here? Resistance is not given. What's the resistance of this circuit? What do you think? Yes, Jesleen, Muniba, Zainab. What should I put it in the denominator? I think before Zainab came, Jesleen and Muniba, you have just written something. Now open your cameras, all of you, and unmute yourself and start answering in the class. Yes. What's the resistance of the circuit? XL, exactly. See, this is a pure inductive circuit. What did I tell you in the last class? Pure inductive circuit, its resistance is XL. Like for resistors, you have no resistance R. So for inductors, it is XL, and for capacitors, it is XC. So the way you use resistors, make it in a habit of using them in the resistors as well. So that's why I've put the unit as ohm. So this is XL. So VRMS is 220. This is 220 divided by XL is this whole term, which is 25 into. This is 10 to the power minus 3. This is 10 to the power 2. So 10 to the power minus 1 into 3.14. So basically it is 2.5 into 3.14 something. So whatever answer you get, this much ampere will be your final answer. See, if question says pure inductive circuit, pure capacitive circuit, something like this the question needs, then make your mind the way you use your usual Ohm's law for the DC current, DC circuits. Similarly, you have to use it here. But if it's not mentioned, then see, is there any other device connected or not? Because you will have LCR circuit also where everything will be present. So you'll have to identify. And start treating XL, XC like the usual resistances we take, because these are completely new terms for you. So have you understood this question? All right. Okay, one more numerical we'll practice before moving on to the LCR circuit. Please write down this question.
Done.
Others have also written. Ghislaine, Zainab.
No, ma'am.
Just complete it and let me know.
Done, ma'am.
Okay. One more question. Let's practice. See, this says a coil has an inductance of 1 Henry. So inductance is given. This is not inductive reactance. Inductance means L is given. That is 1 Henry. Now, what will be the frequency? What will be the frequency? Will it have a reactance of 3142? Means reactance, inductive reactance is given as 3142 ohm. It says what will be the frequency. Frequency, when it says, it means linear frequency, because for angular frequency you have to specify. Whenever anything is not written, that is by default for the translational one, like displacement. So that is your usual linear displacement. When angular displacement is there, it specifies angular displacement. So there is one formula for XL, that is omega L. Omega is equal to 2 pi nu into L. So from here you can easily calculate linear frequency will be XL divided by 2 pi, and L will go in the denominator. XL is given as 3142 ohm divided by 2 into pi is 3.14. So I think these will be cancelled itself. Yeah, they'll cancel themselves because L is also 1. So this will be around, if we take, this is also 3.142 only when we take the value of pi. So this is 100. So 100 by 2, almost the answer will be 50 hertz. Exact value you can calculate it later. Right now you can put it as 50 hertz. Second part says, what should be the capacity of a capacitor which has the same reactance at that frequency? Means at the frequency which we have calculated, value of capacitative reactance is also the same. Means it is also 3142. So capacitative reactance is also 3142 ohms. Frequency is given as 50 hertz because it is taking the same frequency. Now, can you tell me which is the variable here? What do we have to find out? Which variable? L is missing. What is missing? What is the symbol for this? What do we have to calculate, class? Look, read the question, read the line. Yes, Jesleen, you were answering something?
The capacity.
Yeah, capacity. Which symbol? Remember your second chapter, class, electric potential and capacitance. Capacity of a capacitor is what? It's capacitance. C is missing. Like this, class, you will be knowing everything. And when it will come to apply the formula, you will be just knowing the formula and everything, but you won't know what you have to calculate. See, the variable C is missing here. Capacitance is not given. Okay. So Xc is equal to 1 by omega C, which is 1 by 2 pi nu C. From here, C is equal to 1 by 2 pi nu into Xc. Now you can calculate this later. This will be 2 into 3.14 into 3142 into Xc is the same. Frequency is 50. So this much of unit. What should be the unit? Yes, Zainab, unit of capacitor. Jesleen, yeah.
Farad.
Farad, exactly. Correct. Farad plus capacitance. Recall your second chapter. Okay, capacitor is the usual capacitance that we have studied. It's just that C is connected over here. Okay. All right, now we'll start with LCR circuit. Write down this question. And if there's any trouble with this, please let me know. Done?
Yes, ma'am.
All right. So see, basically, series LCR circuit is what? You have studied the resistors, inductors, and capacitors separately. Now you connect all the three of them in series. Here is your resistor, this is your inductor, and this is the capacitor. This is known as LCR circuits, and usually this is the series LCR circuit because all these are connected in series. Now, for resistance, we already know the voltage and the current are in the same phase. For the voltage of, or let me just write it here. So current and voltage are in the same phase. Now the voltage and current of the inductor. We know here the current leads by 90 degree and the voltage lags by 90 degree. Coming to capacitor, here the EMF leads by 90 degree and the current lags by 90 degree. Now, when we talk about the voltages of each, the voltage of the resistance, this is equal to I into R. Voltage of the inductor is equal to I into XL. Voltage of the capacitor is known as I into XC. Okay, so see, when you have all these present together, so there will be a net resistance of the entire circuit, net voltage of the entire circuit. That is what we have to calculate in here. So here the phasor diagram will be a little different. Let's say this is the resistance, this is the voltage due to the inductor, because in inductor the voltage leads, and here this is the capacitor one. Okay, I have written here opposite. Right? This is voltage, this is current, this is current, this is the voltage. Now see, how will we decide the phasor diagram here? See, resistance will be there at its place. But what about VL, VC? See, these are two phasor exactly in the opposite direction. So two possibilities are there. See, either we can have VL minus VC, VL minus VC, where the net direction will be towards VL. Or we can have VC minus VL when the net direction is towards VC. Means if I say, let's say VL is greater than VC, then we can use VL minus VC, or same thing XL minus XC for the voltage and the resistance. So how my phasor diagram will look like? The phasor diagram will look like this. This is the voltage due to the resistance. But see here, since the inductor one is greater, so this will point, the VL minus VC will point in towards the inductor side. Second possibility is there, what if VC is greater than VL? So you will have VC minus VL, which will give rise to XC minus XL. So here you will have the phasor. See, the phasor will be, this will be the voltage due to the resistance, and VL minus VC will be pointing here. VL minus VC will be pointing here. So two cases will be there all the time. So what we do to derive the net resistance of the circuit, we draw an impedance triangle. So this derivation I'll tell you later. First you write down these introductory lines, then I'll discuss the derivation of the net resistance of this circuit. Please write it first.
Done. Done.
Yes, everybody done? Others too?
No, ma'am.
No, ma'am.
Done, ma'am.
Now have you all completed? Others, Zainab, Jasleen?
Done, ma'am.
Done. Zainab, written?
Yes, ma'am.
All right. See, now let's come to the derivation of the impedance triangle. Here also we'll see two cases. Derivation for one case we'll do, and that you can do for the next case as well. See, here we have impedance triangle basically is just a triangle which is used to represent all the three things together so that you can apply your Pythagoras theorem. So see, if I have the triangle in this manner, let's say this is the net EMF of the circuit, E naught. Okay, this is the net EMF of the circuit, which is E naught. R is the resistance, voltage will be VR. XL minus XC will be there because XL is greater. So this will be VL minus VC. The voltages I have written. Now see, the net resistance of the circuit is this Z, which is represented through the symbol Z, is the impedance. XL, XC, and R are the different values of the resistances of individual circuits. When you have them all together, so that will be the net resistance of the circuit is called as the impedance. Impedance means resistance. The actual meaning of the term impedance is resistance. But here, resistance of what? Impedance here in physics is used specifically for the resistance of the LCR circuit. Because three individual resistors are there. XL is also there, XC is also there, R is also there. But in literal term, impedance means resistance. Okay, so how will we derive this? See, we'll apply the Pythagoras theorem here. So when you apply the Pythagoras theorem over here, we can say E naught square is equal to E. This is the hypotenuse, so perpendicular square plus the base square. So we can say VL minus VC whole square plus R square. Okay. Now we'll replace with the values of current here. Let's not replace it here. Let's leave it as it is E naught square. This can be written as I naught into the resistance here is XL. Okay, minus. Here current is I naught into XC whole square. What have I written? These ones only. Here, IR, IXL, IXC. Okay, the same ones. Plus resistance here, this is also VR square. Sorry, not the resistance. Resistance now will come when we are talking about the voltage. So voltage across the resistor, which is VR. So that is equal to I naught into R whole square. Now we can take I naught square common from all of these. That will be, if I naught square is taken common, here XL minus XC square will be left. From here, R square will be left. If we take I naught square common. Now plus I naught can be I naught whole square. This can be written as E naught square divided by this whole term, XL minus XC square plus R square. So I can, if I take the root on all the sides, I can say I naught is equal to E naught divided by under root of all this term, XL minus XC plus R square. Now compare it with Ohm's law. Current is equal to voltage by resistance. So basically, the resistance that we have here is impedance, which I was telling you. Impedance means the net resistance. This is equal to under root XL minus XC whole square plus R square. But what if XC was greater than XL? Same thing, C class. You will just have XC minus XL. Same derivation, if XC is greater than XL, VC is greater than VL, then same thing, Z will be equal to XC minus XL whole square plus R square under root. That will be the only difference. So this is the resistance, a very small derivation and an easy derivation class. We have just used the Pythagoras theorem. That's it. Geometry is only used here. Geometry, then Ohm's law, take the current out, again compare it with the resistance. So this is your total resistance of the circuit. Okay, net resistance of LCR circuit. Now in two cases that depends. So yes, you were asking impedance. So it's the effective resistance of the series LCR circuit which opposes or impedes. Impedes means to oppose resistance, okay, as the flow of current through it. Okay, so this is represented as Z. So when you have to calculate the value of tan phi, means see phi is the phase angle. So if you have to calculate phase angle, that can be given through tan also, cos also. So for tan you can use XL minus XC by R, or you can use tan phi is equal to VL minus VC by VR. This can be used, or you can use the common value cos phi is equal to R by Z. That will be there in both the cases. And here if we refer to the value when XC is greater, so this will be XC minus XL by R. Or if in terms of voltage you want to write, that will be VC minus VL by R. Cos phi still here will be R by Z. So the derivation is not based on some physical meaning. This is just based on the trigonometric value. Okay. See, XL, when XL is equal to XC, this is a condition which is known as resonance. That we'll do later. After this part only, we'll discuss what is resonance. LCR circuit and resonance are the most important topic. So there VL, VC will be equal, and we say there is no phase angle. So if there is no phase angle, that means it's a purely resistive circuit. Okay. Now see, like we use no, I is equal to V by R. If it is only resistive, we use E naught by R. If it is purely inductive, we use E naught by XL. Purely capacitative, E naught by XC. Here, LCR is there. So you use impedance as the net resistance. Like when you were in 11th class, different vectors were present. Now forget 11th. In 12th also, when you had electrostatic forces, net different magnetic fields were there, different electric fields were there. What did you used to do? You used to add all them vectorically, and then that would have been the resultant. Similarly, the net resultant of all the resistances is given by this. Now we cannot use parallelogram law here because these are all scalar quantities. Resistances are scalar. So what have I done? I'll just repeat. Impedance means the way we have the resistance of individual circuit. When we talk about the term resistance means opposition. When the electrons are flowing smoothly, then the ions present within the wires, they oppose the flow of current. That is resistance. So for different circuits, you have R, you have XL, you have XC. These are the three resistances of individual circuits. When you combine all of the three in series, all the three devices, you have to get a net resistance of the circuit. That is given through Z is equal to under root XL minus XC or XC minus XL, depending on its magnitude square, plus R square. And impedance is the opposition to the flow of current. And to calculate the phase angle, again you can use geometry to use tan theta or cos theta. Tell me, is it clear till here to all the three of you? Muniba, Jesleen, Zainab?
Yes, ma'am.
Ma'am, can you explain the tan and cos phi?
Yes. See, this is basically the phase angle. See, I'm repeating, this is not a physical meaning based derivation. This is just a geometrical derivation for our convenience. That's all. So this is the angle, phase angle of the circuit. So if I calculate, see, here also I had the same diagram, XL minus XC. This triangle is known as the impedance triangle, which was developed for its derivation only, because this was derived through experiments. So now if you calculate tan will be perpendicular upon base XL minus XC by R, or in this case XC minus XL by R. I also wrote VL minus VC and this as VR. Similarly, VL minus VC here, VL minus VC by VR. Same thing. Just the value of tan theta I have written. I also told you this can be written in terms of voltages also. The same normal perpendicular upon base, and for cos theta, same thing, base by hypotenuse, so R by Z. Now clear?
Yes, ma'am.
All right. Jasleen, you also understood? Have you?
Yes, ma'am. Yes,
All
ma'am.
right. Please write the derivation, class. Numericals often come from this chapter, and among the derivation of the impedance can come. Then you have the derivation of a quality factor. That is very important. So we'll discuss that later. But first write it in here. No. Then it is not the power factor. Power factor is only cos phi. Cos phi is known as power factor. Tan is just a simple tan of the trigonometry that we use. That's it. Just to calculate phi if we are unaware of R and Z. But power factor is just cos.
Ma'am, can you scroll? Ma'am, we need feedback.
Are you asking to scroll down, Muniba?
Yes, ma'am.
Ma'am, can you scroll up?
Mhm.
Done.
See, it is determine the impedance of a series LCR circuit if the reactance of C and L are 250 and 220. Means XC is given as 250 ohms and XL is given as 220. Resistance is given as 40 ohm. So plus clear cut, we can see XC is greater than XL. All right, so XC minus XL will be 250 minus 220, that is equal to 30 ohm. So what do we have to calculate? Impedance will be XC minus XL square plus R square under root, which will be 30 square plus 40 square under root, which is equal to 50 ohm. So this is the final circuit net resistance of the entire circuit. Okay. Yeah, easy question, formula based.
Yes, ma'am.
ma'am.
Write it. Now we'll move on to resonance topic.
Done, ma'am.
All right, others, have you already so written or still writing? Done or right, Jasleen Zainab?
Done, ma'am.
All right. Jasleen, you too? Okay. See, there's a condition when the inductive reactance and capacitive reactance are equal to each other. When they are equal, so what will happen? See, this is the formula of Z, under root R square plus XL minus XC square. So if they are equal, they'll cancel each other. So Z will be equal to root R square. So we can say Z is equal to R. Now see, impedance, what is happening? You were getting a greater value. Something was getting added in the denominator. So you were getting a greater value. Now it's just equal to R. Like look at the previous question which we saw. This, they gave the whole impedance as 50 ohm, while the resistance was only 40 ohm. So impedance is decreasing. So what will happen? See, current is equal to EMF by the impedance. So if your impedance is very low, so current will be very high. So Z, if it is low, I is high. So a series LCR circuit is said to be in resonance when the current through it has the maximum value. Okay, so this is the actual definition, that current will be maximum, impedance will be minimum. But to understand and for your understanding part, resonance in impedance, resonance is high. In impedance, resonance is high, or resonance is the condition. Impedance is low. In
And then
resonance, I think you were asking, in resonance is the impedance high?
yes, ma'am.
Yes. No, it will be low. See, how can the impedance be high? If here current is high, current will be high and Z will be low. Then only, see, you see, XL and XC, they are cancelling each other. So what will happen? Your denominator is getting reduced. Like in the previous example that you have written, the question that you have written, there Z was 50 ohm if it was calculated through everything. But if it is just equal to R, what will you get? You will get the value of Z equal to the resistance. That was just 40 ohm. So impedance decreases and current increases. So you get a very high value of current. The resistance is low because current and resistance are inversely proportional to each other. So impedance is maximum while the current is, impedance is minimum while the current is maximum. What about its frequency? See, if Z is equal to R, what this frequency one is very important, class. Look, L is equal to XC. So this means omega L is equal to 1 by omega C if I write their values. Now let's just interchange. If I just shift it here, I can say omega into omega is equal to 1 by LC. That means omega square is equal to 1 by LC. That means omega is equal to 1 by under root LC. And what is omega? That's the angular frequency. Angular frequency. Now, omega is equal to 2 pi nu. So what will be the linear frequency? Omega divided by 2 pi. So linear frequency comes out to be 1 by 2 pi under root LC. This is the formula, while this is our linear frequency. This is the formula of linear frequency. So this derivation often comes of this frequency. So basically, you remember for your calculation part, whenever you see this, this is the condition of resonance for you. This is resonance that acts. Okay, this is the resonance. So you can write down and calculate many things using this concept. We'll practice numericals also based on this. This question at least we will do if we have time. So write down the theory part. Let's see how much time is left. And it's a very, very important topic, class. This question was actually based on resonance only, so that's why I've left. Both were equal, XC and XL were equal. That we can do later. Please write it from here. Is this clear? Muniba, Jasleen, and here, resonance part.
Yes, ma'am.
All right, please write it. Written till here?
Yes, ma'am. Done, ma'am.
Okay, then.
When
Class.
it's done.
Okay, write it then. Let me know once completed.
Done, ma'am.
All right. I'll stop
One
here.
second,
From
ma'am.
this topic only, I'll continue in the next class. Okay. All right. Thank you, class 10. Okay, bye.
Thank you, ma'am. Allah Hafiz.
1 second, ma'am. I'm not done writing.
Yes, Justine, take your time.